Alright, hi and welcome again. Today we are talking about AVL trees. As usual, you find the link for the Git repo where you find the source code down in the description below. I will separate this video into two parts because the implementation will take a little bit longer. So today we will implement the basic tree and talk about the theory. And tomorrow we are going to have a look at the actually rotation, and so let's start right into it. Alright, so an AVL tree is basically a binary search tree where all nodes in the left subtree of a node are smaller than the value in the current node, and all elements in the right subtree are greater or equal than the value in the current node. But the speciality of the AVL tree is that we have a height restriction in our subtrees, and that means that the left subtree of a node is always like 1 higher or lower or equal, but the difference is not higher than 1. Alright, and it has with that a search time of log n in average and worst case. And it is an improvement on the binary search tree in that chance that we don't have the list structure as we would have in a binary search tree. Meaning that it is forbidden that we can have a list of elements compared to a real tree, and that is through the restriction in the height of the subtrees. Let's have a look at first at the binary search tree. If we insert these elements here, the 5, 8, 6, 9, 12, 4, 1 and 3 into a binary search tree, then we would insert the 5 at first, then the 8, then the 6, then the 9, the 12, the 4, the 1 and the 3. In this order here you see already that all the elements left of the tree or of the current node are smaller than the value in the current node, and all on the right are equal or higher. If you want to see a video about binary search tree, up here you can see a video I blended in. And so that is also a really good video on binary search trees itself. Alright, but let's have a look at this part of the binary search tree. And there we see that the left child of the 5 is a 4. There we have a height of 2. So the left subtree of the 5 has a height of 2. And the right subtree is much bigger, so it has a height of 4 actually. And that is an imbalance in the tree, and that reduces the runtime in search and insertion and stuff like that. So what we basically do in our search tree here in the AVL tree is a rotation, and that means that we rotate the 8 where the 5 was, we append the 5 to the 8 then, and we append the 6 as a right node to the 5. So, and with that we achieve this tree. But there is a certain condition on that, and that is that the subtree on the right in this case of the 8, the 6, the right, the left, so it's from the 5 the right and then the left it is the 6. This subtree must be smaller or equal than the right subtree of the 8, and that is written down here. So we have a left rotation, there's also a right rotation that mirrors this behavior, and the left subtree of the 8 must be smaller than the right subtree of the 8. And that is called right-right situation, because the right subtree of the 5 is called it's right heavy, and the right subtree of the child of the 8 is also right heavy. That's why it's called right situation. Alright, let's have a look what happens if this condition is not there. Then we might have such a tree here. As you can see, we have again the height of 2 for the left subtree of the 5 and the height of 4 for the right subtree. But now if we look at the 8, there we have the left subtree of the 8 is actually bigger than the right subtree of the 8. And that is a little problem, and there we need a different approach. So what we do here is we do at first a right rotation on the 8 so that we have the right child of the 5 will be 6, the right child of the 6 will be 8, and the left child of the 8 will be 7. So if we do this first right rotation, then we end up like this, and then we do our left rotation as usual. So with this double rotation, in the first step we make the condition for the left rotation, and in the second step we do actually the left rotation. So if we do that, we end up in here after the double rotation with this type of tree. We have the 6 in the top and the 5 and the 8 as the children. Alright, so and the condition for that is that we have, or that the left height of the subtree of the 5 is smaller than the right, and the left subtree of the 8 is larger or equal to the right. And that is also called a right-left situation, because the right of the 5 is, or the 5 is right heavy, so it has like a greater height there, and then the right child of the 5 is left heavy because it has more children on the left side than on the right. Alright, so let's get in and implement it now. For that, I at first create a new file called AVL tree.python, and there I create a class AVL tree. In there I want now a helper class that creates me the actual nodes. So I create a class called __node to make it private, and there I want at first the value of the node, and I set that to none in the beginning. Then I want the left child as none and the right child of none. And the right child of the node, not of none. And additionally I want to store the height of the left subtree and the height of the right subtree in this node. So there I say height left, I set that also none for now, and I say height right, and I set that none for now. Alright, and I also want to create a constructor there just to save me some time when I instantiate the nodes. And there I say init, and it gets the self property, and it will get the value, the height left and the height right. And now we can set those self.value equals the given value, self.height left equals the given left, and self.height right is equal to height right. Alright, so now we have this helper node. What we also need is a root of the tree. So we create the root and say this is for now none. Okay, so good so far. Now we can finally insert our elements. And there I say def insert. That gets a self property and a value. And we make some documentation here and say inserts an element in the tree. Alright, at first we can check if our root node was already set. If not, we just give it the value and then we are fine. So if self.root equals none, then we go in and say self.root, and now we create an instance of our node class, our helper class, and say self.node, and that gets the value. And here we can say, because we don't have any subtrees now, the 0 and the 0 in the height. And I have to use here a double equal sign. And so we set our root node and we can return. Okay, now that we have the root node, we can traverse through the tree and see whether we have to append it the value on the left or on the right of the node. So at first I want to create a variable called current node, and there I initialize it with our root node, because we want to start traversing at our root node. And then I say for now while true, and that is my exit condition for now. And in there I want to check at first if we have traverse to the left or to the right. So I say if current node dot value, and let me actually put the value in front. I'm used to that. You might do that differently, but I want to stay consistent with that. And if that, we go to the left side of our current node. So traverse to the left. If this is smaller, then we can check if our current node is a leaf. So if, or our current node left is a lead, current node.left, and we initialize it with none. So we say none. We can also see that here that we say left is none and right is none. So here we can say is a leaf. Then we need to instantiate this tree, this leaf. So we can say here current node dot left is, and now we have to instantiate it with our node class again, and there it gets none for now, 0 and 0, because the leaves will always have a height of 0. And then here we can say current node equals our current node dot left. Alright, so good so far, but we didn't insert the value yet, but we come to that in a minute. Let us do the traverse to the right first, and there we say else. Now we know our value is greater or equal to our current value. So we say again, here is a leaf, and there we go in and say current node dot right equals none. Then we go in and say current node dot right equals, and there we instantiate the right node. And we give again none, 0 and 0. And then we can say current node equals, and that is current node dot right. Okay, so good so far. Now we actually traversed the tree and we are at the leaf where we want to insert the value. So I go above here and say if, and there I say current node.value equals to none, meaning it is a leaf. Here we can say we are at a leaf. Then I want to set the value there, and there I say current node.value equals to value. And then I go in and say return. So with that, we insert the value at the right place after we instantiated the tree. Okay, from there I want to create now a print method that prints our tree. For now it is simply a binary search tree, but we will do that AVL property later. So we say def print, and I want to print that in breadth first traversal. So that just gets self, and here we can say print the tree in breadth first traversal. And I actually want to put a method in here in our node, and that is the print method. And I say here def print, and that simply gets self, and we say here return, and that returns us a string of the properties, and we format this string then. And at first I want the value. Let me do this here. Then we want the left node of it, or the left value. Then we want the right value. And we also want the height left, and we want the height right. Alright, and let me go into a new line here. Our value is self.value. Our left is, there I want to go in here and say self.left.value, but only if self.left is not equal to none. And if it is none, I want to put none there. And we do exactly the same for our right. So we can replace the left here with right. And then I go in and we want the height left, and that is self.height left, and we want self.height right. Okay, so good so far, and now we can print our actual node. And here I go in and I say if our root node is none, then I want to print none. So I say if self.root equals to none, then I want to print none, and I want to return here. I don't want to do anything else. Other than that, I want a current node. Oh no, I want a queue actually, because we want to do that in breadth first traversal. So we say our queue is initialized with our root node. And then we can go in and say, well, our queue is not empty, and that is the same as our length of our queue is greater than 0. In the next step, I want to get the first element from our queue. So I say current node equals, and there I say queue 0. So we work now on our first element in our queue. And since we are done after this actually step in the loop, or with this part of the loop, so we can remove this node already from our queue. So I say 1 to the end, which basically means that we remove the first element. Alright, and then I say here current node dot print, and here I say print current node dot print. So we print this node. And what else do I want to do? Now I want to insert the children of the node. So I say if there are not none, then it is fine. If current node dot left is not none, then I say queue dot append current node dot left. And I want to do exactly the same with the right node. So we go in and replace this with our right node. And in the end, we are done with printing our tree. Alright, let's try it out so far. If name equals main, we go into our main class. And there we create a new tree instance of our AVL tree. And then we need some data that we want to insert. Let's take our example here that we had earlier. That was 5, 4, 8, 6, and then we had 9 and 12. Alright. And then I say for every value in our data, I want to actually insert that into our tree. Tree.insert our value. And then I go in and say tree.print BFT. So let's see if that works so far. And there we are. The 5 is a root node that has left 4 and right 8, and the height is okay. The 4 is the left node and has a height for now of zeros and has no children. The 8 has a left node and a right node with a height of 0, and the 6 is the left node of the 8 with no children. The 9 has only a right child, the 12, and the 12 is a leaf node again. Alright, so good so far. So that actually works. So if we are here, then where were our insert method? Here. So here we also want to adapt the height of the tree now. Because if we are at a leaf, then we have to, or if we insert a new leaf, then we have to check if we have to insert or if we have to change the height in the tree. And for that I use a def first search, and I say def. And here I make that private and set adapt height. And that gets self and our current node. And we can say here adapts the height of the tree in that first traversal manner, and we make here a full stop and we put a recursive there so everyone knows that goes recursive. Alright, so what we have to do first, we check is the node we are currently at a leaf node. So if node.left equals to none, Then we set the height of the left subtree to 0. So we say node.height left equals to 0. If not, we want to keep going with our left subtree or into our left subtree. So we say node.height left is equal to, and now we call our method recursively adapt height of node.left. Okay, so good so far, and now we do exactly the same for our right node again. So let me put that down here below. And we have left here, and we make there a right out of it. And since it replaced it here with a small r, we have to change this. Alright, so good so far. Now we just have to tell the parent what is the maximum height of the right and the left subtree, so it can set it. So here we say return, and we actually want to return the maximum, so we use Python's max method, and there we want node.height left, and since the parent will the height 1 greater, we can add 1 here, and we want the height of the right one, so we say height right, and there also a +1. So when we go in here into our insert method, then we go here and say self.adapt height, and we actually want to adapt our height from our root node on. So we say here root. Alright, so let's check that if that works. So we should see changes in our height. And as we can see, the 5 has a height of left of 1 and height right of 3. And the 4 has both heights of 0 as a leaf. The 8 has left of 1 and the right of 2. And that looks very, very good. Okay, so now we have implemented the basics of the tree. So we will keep going with the rotation in the next video. So if you liked this video, give it a thumbs up and subscribe to the channel so you get informed whenever I'm uploading new videos. I really appreciate if you tell me down in the comments below what you think about this video and if it helped you or what I can improve. So I'm really excited about your opinions, and we see each other in the next video. Have a great day. Bye.